There was a time when cities adapted to the land. Rivers set boundaries. Mountains slowed ambition. Coastlines marked the edge of what could be built. That era is ending. Across the planet, humanity is no longer negotiating with geography. It is redesigning it. Coastlines are extended with sand and stone. Oceans are crossed by continuous steel corridors. Rivers are stopped, lifted, redirected, and converted into data, energy, and control. What once defined limits is now treated as a variable. These megaprojects are not monuments in the traditional sense. They are systems-engineered environments where physics, logistics, automation, and governance merge into a single operating logic. Their scale is so large that failure is no longer local. A crack, a delay, a miscalculation echoes across economies, ecosystems, and entire regions. Technology has changed the rules. Robotics replace human presence. Sensors feel stress before eyes can see it. AI manages flows of water, electricity, traffic, and time. Construction no longer stops at height, depth, or distance. It only pauses at complexity. Yet with every new structure, the question shifts. Not can it be built, but what does it replace? A river becomes a reservoir. A desert becomes a grid of mirrors. A coastline becomes a blueprint. This is a journey through the world's most ambitious megastructures, not as a celebration of size alone, but as an exploration of how far human systems have moved beyond human scale. From iconic skylines to autonomous infrastructures, from artificial land to planetary machines, from earthbound engineering to constructions that orbit in silence, these are not just projects of the future, they are signals. Markers of a civilization testing the outer limits of control and discovering that the higher it builds, the more carefully it must balance power, precision, and restraint. Dubai Frame does not compete for height or mass. It competes for perspective. Rising 150 meters above Zabil Park, this monumental rectangle was designed not as a tower, but as a concept made structural. Two vertical columns and a horizontal bridge form a perfect frame, an object that does nothing until you look through it. And when you do, the city becomes the subject. On one side lies old Dubai, low-rise neighborhoods, historic souks, narrow streets shaped by trade and climate. On the other stands the modern skyline, glass towers, highways, and vertical density powered by capital and energy. The frame does not explain the transition. It simply holds both realities in place, forcing them into the same field of view. Engineering precision defines its impact. Laser alignment and millimeter-level GPS positioning were used to ensure exact right angles across the entire structure. Any deviation would collapse the illusion. The frame must be perfectly balanced to function symbolically. Inside, the experience is sequential. Visitors move upward through an enclosed vertical gallery that narrates the city's past, then step onto a transparent glass bridge nearly 150 meters above the ground. Beneath their feet, the city drops away. The body hesitates. The skyline does not. Dubai Frame belongs to the human-scale icon layer of mega projects. It does not dominate terrain or redirect resources. Its power lies elsewhere in narrative control. It transforms urban history into a physical axis, turning time into something that can be crossed. Unlike other megastructures, the frame does not promise a future. It measures one. By standing still, it forces comparison. By framing space, it defines ambition. In a city built on constant forward motion, Dubai Frame performs a rare function for a megaproject. It pose. Burj Khalifa is not simply tall, it is a vertical system pushed to the edge of physics. Rising 828 meters above the desert, the tower was never about height alone. It was an experiment in how far architecture, materials, and computation could stretch before gravity, wind, and heat reclaimed control. At this scale, the problem is no longer building upward. It is keeping the structure stable, habitable, and predictable in an environment that resists all three. The tower's spiral Y-shaped design is not aesthetic ambition, it is aerodynamic necessity. As the structure rises, each tier subtly rotates, disrupting wind vortices that would otherwise amplify oscillation. More than 7,000 wind and structural simulations were conducted to prevent resonance that could render the building uninhabitable. Inside, Burj Khalifa operates as a vertical city. Over 160 floors contain residences, offices, hotels, mechanical zones, and observation decks, all supported by pressurized water systems capable of lifting millions of liters daily to extreme heights. At the upper levels, air pressure, temperature, and even human comfort become engineering variables rather than givens. Construction itself bordered on logistical improbability. Concrete had to be pumped higher than ever before, at night, to avoid daytime desert heat that would cause premature curing. Cranes operated in wind conditions that could bend steel and halt work instantly. Yet Burj Khalifa's significance extends beyond engineering. It redefined what a skyline could signal. In a single structure, Dubai compressed global capital, tourism, and symbolic power into a vertical line visible from nearly 100 kilometers away. Burj Khalifa belongs to the limit of height layer of mega projects, where human presence is still possible, but only through constant technological mediation. At its summit, the city below feels unreal. Cars shrink into motionless threads. The desert fades into abstraction. Here, height is no longer about view. It is about how much system is required to let humans briefly occupy the sky. Marina Bay Sands is not a single building. It is three towers, forced to behave as one system. Rising from reclaimed land at the edge of Singapore's financial district, the complex is defined by its most improbable element, a 340-meter sky park resting across the tops of three 55-story towers. At this height, the structure is no longer governed by architectural convention. It is governed by load transfer, thermal expansion, and millimeter-level tolerance. The sky park weighs more than 7,000 tons. It is not rigidly fixed. Instead, it is engineered to slide and flex independently, allowing each tower to move under wind and heat without tearing the structure apart. Expansion joints, shock absorbers, and hidden bearings absorb motion that visitors never see but would immediately feel if they failed. Below, Marina Bay Sands functions as a self-contained urban machine. Hotels, convention halls, theaters, shopping districts, and transport links are stacked vertically and horizontally, designed to circulate people continuously without congestion. Energy, water, lighting, and security are managed through centralized digital systems that operate around the clock. The infinity pool at the roofline is not just spectacle, it is a visual illusion, engineered with precise edge geometry to erase boundaries between water, sky, and city. From this height, the pool does something unusual. For a megastructure, it removes reference points. The skyline dissolves. Depth becomes uncertain. Marina Bay Sands belongs to the integrated urban icon layer of megaprojects. It does not dominate through height or mass, but through coordination. Every component, structure, experience, circulation, and symbolism is synchronized. This is not architecture that adapts to a city, it organizes one. By placing leisure, commerce, and spectacle into a single elevated plane, Marina Bay Sands demonstrates a new ambition in mega-project design, not just to build higher or larger, but to compress an entire city's functions into a controlled, elevated ecosystem. Here, the future of cities is not vertical alone, it is systemic. Ain Dubai is not built to move people quickly. It is built to slow the city down. Standing 250 meters above the Persian Gulf, the wheel is the largest observation wheel ever constructed. Its scale turns a familiar amusement concept into a megastructure governed by structural dynamics rather than entertainment logic. At this diameter, rotation becomes an engineering challenge measured in stress distribution, wind tolerance, and fatigue over decades. The wheel's hub and spokes were assembled using some of the largest cranes ever deployed, lifting steel components weighing thousands of tons in open coastal conditions. Salt air, constant wind, and temperature variation forced engineers to treat corrosion and vibration as primary design constraints, not secondary concerns. Each of the 48 cabins functions as a sealed environment. They are climate-controlled, balanced with extreme precision, and attached to the rim through load-bearing joints designed to absorb movement without transmitting instability to passengers. The structure must remain perfectly aligned. While rotating continuously, any asymmetry would magnify forces across the entire system. Ain Dubai belongs to the human-scale spectacle layer of mega-projects, but its intent is more subtle than visibility alone. By elevating observation into a slow, circular motion, it transforms the skyline into a narrative rather than a panorama. The city unfolds gradually: desert, sea, towers, and horizon, passing in sequence rather than all at once. From the cabin, Dubai appears suspended. Roads lose urgency. Towers lose dominance. The city becomes geometry and light. Unlike towers that assert vertical conquest, Ain Dubai emphasizes control through balance. Its power lies not in resisting gravity, but in negotiating with it continuously, minute by minute, rotation by rotation. This is not a structure that celebrates speed or dominance. It celebrates precision, patience, and equilibrium. A megaproject designed to remind a city defined by acceleration what it feels like to pause above itself. The Shard does not dominate London by force. It emerges from it, rising 310 meters above the Thames. The Shard was designed not as a solid tower, but as a fragment of light, an architectural decision that defines its entire engineering philosophy. Instead of a sealed monolith, the structure tapers upward into exposed glass fins, allowing wind, cloud, and sky to pass through its upper edges. This openness is not aesthetic alone. At such height, London's unpredictable wind patterns become a structural threat. Engineers responded with a tapering form and a flexible steel core that allows controlled movement, reducing pressure rather than resisting it. The building is designed to bend, not fight. More than 11,000 glass panels form its facade, angled to reflect shifting light conditions. The tower changes color throughout the day: steel, gray at dawn, silver at noon, amber at sunset, blurring the line between structure and atmosphere. In rain or fog, it partially disappears, reinforcing its intended role as a vertical extension of the sky rather than an object imposed on the city. Inside, the Shard functions as a vertical ecosystem. Offices, residences, hotels, and public observation spaces stack upward, like layers of altitude rather than floors. Environmental systems adjust airflow and temperature based on elevation, reducing energy use by allowing natural ventilation in the upper levels, an unusual feature for a skyscraper of this height. Unlike megastructures built to proclaim national power, the Shard reflects London's historical restraint. It does not overwrite the skyline, it punctuates it. Old brick districts, historic bridges, and low-rise neighborhoods remain visible and legible beneath it. From the observation deck, London does not appear conquered. It appears assembled a patchwork of eras, textures, and intentions. The Shard is not a monument to speed or scale. It is a study in vertical humility, proving that modern megastructures can rise into the future without severing their connection to the past. The Petronas Towers were never meant to be just tall. They were meant to redefine where modern Asia stands. Rising 452 meters above Kuala Lumpur, the Twin Towers were completed in 1998 as the tallest buildings on Earth at the time. But their significance lies not only in height, it lies in symbolic engineering, where structure, culture, and national ambition were fused into a single vertical statement. Unlike Western skyscrapers built on steel frames, the Petronas Towers rely primarily on reinforced concrete, a deliberate choice shaped by regional material availability and seismic considerations. At this scale, concrete behaves differently. Engineers developed one of the deepest foundations ever attempted. 104 piles drilled more than 120 meters into unstable limestone and cast rock, where voids and underground caverns forced continuous redesign during construction. The tower's floor plan is based on an 8-pointed star, derived from Islamic geometry. This was not decorative symbolism. The geometry distributes load evenly while embedding cultural identity directly into the building's structural logic. Architecture becomes ideology, translated into physics. Connecting the two towers is the Sky Bridge, suspended at levels 41 and 42. Unlike rigid bridges, it is not fixed at both ends. It slides slightly as the towers sway independently under wind and thermal expansion, preventing catastrophic stress buildup. The bridge is not a bond, it is a buffer. From the ground, the stainless steel and glass facade reflects tropical light like a moving surface. By day, the towers shimmer. By night, they become vertical beacons, anchoring the city's skyline with symmetry and calm. Inside, the towers operate as a corporate and civic engine, housing offices, public spaces, and cultural institutions. They were built not to isolate elites, but to announce a rival that Southeast Asia could engineer, finance, and execute projects at the highest global level. The Petronas Towers did not simply break a height record, they broke a psychological one. They proved that modern megastructures no longer belonged to a single hemisphere, and that the center of gravity in global ambition had quietly shifted. Palm Jumeirah is not a building. It is a decision to redraw the coastline. Extending into the Persian Gulf, the artificial island was conceived to solve a strategic limitation. Dubai was running out of beachfront. Rather than expand inward, engineers chose to manufacture land at sea, turning geography itself into an engineered asset. The project required more than 144 million cubic meters of sand and over 7 million tons of rock, placed with GPS precision in open water. Traditional land reclamation methods were impossible at this scale. Instead, dredged sand was sprayed into position and compacted through vibration, allowing the seabed to stabilize without concrete foundations. The palm shape is not aesthetic. Each frond creates maximum shoreline exposure, multiplying usable waterfront while maintaining manageable infrastructure distances. Surrounding the island is a crescent-shaped breakwater, designed to absorb wave energy and shield the interior from erosion. Hidden channels were carved into the structure to ensure water circulation, preventing stagnation in the enclosed lagoons. Building Palm Jumeirah meant confronting long-term environmental forces rather than immediate structural risk. Tides, currents, and sediment drift constantly attempt to reshape the island. Maintenance is continuous. Sand replenishment is not a failure. It is part of the system. Palm Jumeirah represents a new category of mega-project, territorial engineering. It does not rise upward. It spreads outward, converting capital and logistics into land itself. Roads, utilities, and buildings came later. The real structure is the geometry beneath the waterline. From above, the island reads as a symbol. From the ground, it functions as a city district. From the sea, it behaves like a living barrier, negotiating with nature every day. Unlike towers that challenge gravity, Palm Jumeirah challenges permanence. It proves that in the modern era, land can be temporary, adjustable, and maintained by design. This is not conquest of nature. It is coexistence through constant intervention. A megastructure that exists only as long as human systems remain attentive enough to sustain it. The Hong Kong-Zhuhai-Macau Bridge is not a bridge in the traditional sense. It is a regional machine. Stretching 55 kilometers across the Pearl River Delta, the system combines bridges, artificial islands, and a submerged tunnel to connect 3 separate jurisdictions into a single transportation corridor. Its purpose was never convenience alone. It was economic integration at megastructure scale. Open sea conditions, heavy shipping traffic, typhoons, and seismic risk made a continuous surface bridge impossible. Engineers responded by submerging part of the route. A 6.7-kilometer underwater tunnel allows large cargo vessels to pass above, while artificial islands at each end manage transitions between bridge and tunnel systems. Land, sea, and infrastructure are fused into one continuous logic. More than 400,000 tons of steel and millions of cubic meters of concrete were deployed, with prefabricated sections floated into position and locked together offshore. Every joint was designed for fatigue resistance, capable of enduring constant vibration from traffic, waves, and wind over a century-long lifespan. The bridge is engineered to survive Category 1, 6 typhoons, major earthquakes, and ship collisions. Its foundations penetrate deep into unstable seabed layers, where soft marine clay required reinforcement before any structure could exist. Nothing here rests naturally. Everything is calculated. But the most profound transformation is economic. Travel time between Hong Kong and Zhuhai was reduced from 3 hours to under 30 minutes. Entire labor markets, logistics chains, and industrial zones were reorganized around this new geometry of distance. From the roadway, the horizon dissolves into water and sky. The sense of crossing a boundary disappears. That is the project's true achievement. The Hong Kong-Zhuhai-Macau Bridge does not symbolize national pride through visibility. It exercises power through connectivity. This is infrastructure not as a monument, but as strategy, a megastructure designed to quietly reshape how millions of people move, work, and belong within a single engineered region. The Lake Pontchartrain Causeway does not impress through complexity. It overwhelms through duration. Stretching nearly 39 kilometers across open water, it is the longest continuous bridge over water in the world. There are no towers, no dramatic arches, no skyline moments, only an unbroken line of concrete vanishing into the horizon. Completed in 2 phases, between 1956 and 1969, the causeway was built to solve a regional constraint. Lake Pontchartrain separated New Orleans from its northern suburbs, turning short distances into long detours. The solution was radical in its simplicity: built straight across. More than 9,500 pre-stressed concrete spans rest on over 2,200 piles driven deep into the lake bed. Each segment is identical. Repetition, not novelty, is the core engineering strategy. The bridge functions like an industrial assembly line, stretched across water. At its midpoint, land disappears completely. Drivers see nothing but sky and lake in every direction. Orientation becomes psychological rather than visual. During fog or storms, the causeway feels less like a road and more like a controlled suspension over emptiness. Designing for hurricanes was unavoidable. The bridge was engineered to flex under wind and wave loads, with drainage systems and low-profile barriers that reduce pressure rather than resist it. Survival depends on endurance, not dominance. The causeway carries no grand symbolism. It was not built to represent national ambition or architectural innovation. Its success lies in reliability. Decades of daily crossings, storms endured, and economic flows maintained without interruption. Unlike mega projects that announce themselves, the Lake Pontchartrain Causeway fades into routine, and that is its power. This structure proves that scale does not always demand spectacle. Sometimes, the most radical act of engineering is extending a line so far across uncertainty that distance itself stops feeling real. The causeway is not a monument. It is infrastructure as persistence, a quiet reminder that endurance can be more transformative than height. The Akashi Kaikyo Bridge exists because nature failed once, and Japan refused to accept it again. Spanning 3,911 meters across the Akashi Strait, the bridge connects Kobe to Awaji Island over one of the most violent maritime corridors in the world. Strong currents, deep waters, frequent typhoons, and seismic instability make this stretch of sea inherently hostile to construction. In 1955, a ferry disaster here killed 168 people. The bridge was conceived not as ambition, but as necessity, shaped by memory. At its core, Akashi Kaikyo is an exercise in extreme tolerance. Its main span of 1,991 meters remains the longest suspension span on Earth. Towers rise 298 meters above sea level, anchored into seabed foundations, sunk more than 60 meters deep. Each main cable contains over 290,000 individual steel wires, together strong enough to wrap around the planet several times. But the bridge's defining moment came before it even opened. During construction in 1995, the Great Hanshin earthquake struck nearby Kobe with devastating force. The seabed shifted. The two towers moved apart by nearly 1 meter. Instead of collapsing, the bridge absorbed the displacement. Engineers recalculated. The span was lengthened. The structure adapted. This was not resilience by chance. It was resilience by design. The bridge is built to withstand magnitude 8 earthquakes, winds exceeding 280 kilometers per hour, and constant marine corrosion. Its deck incorporates aerodynamic stabilizers that reduce oscillation, while dampers convert motion into controlled dissipation rather than destructive force. Driving across Akashi Kaikyo, the sensation is calm, almost deceptive. Traffic flows steadily, the sea churns far below. The bridge does not dramatize the danger it contains. Unlike megastructures that dominate landscapes, this one negotiates with them. It accepts that movement, uncertainty, and catastrophe are inevitable, and builds systems that survive by yielding intelligently. Akashi Kaikyo Bridge is not a triumph over nature. It is a lesson learned from it. Written in steel, motion, and restraint, the Millau Viaduct does not cut through the landscape. It floats above it. Spanning the Tarn Valley in southern France, the viaduct rises with a lightness that feels almost contradictory to its scale. At 343 meters, its tallest pylon surpasses even the Eiffel Tower, making it the tallest bridge structure in the world. Yet from a distance, it appears thin, restrained more line than mass. The challenge was not simply to cross the valley, but to do so without crushing it. Winds here funnel violently between plateaus. Fog settles unpredictably. The terrain below is protected and largely untouched. Traditional bridge designs would have imposed weight and visual dominance. The solution was a cable-stayed structure so slender it seems to hover. Seven concrete pylons emerge from the valley floor, each tapering upward before giving way to steel masts and cables. The deck was not built in place. Instead, it was incrementally launched from both sides of the valley sections, pushed outward millimeter by millimeter, suspended hundreds of meters above open air until they met with near-perfect precision. Wind, not weight, was the governing force. Engineers designed the deck with an aerodynamic profile similar to an aircraft wing, allowing gusts to pass over and under without inducing dangerous oscillation. Sensors embedded throughout the structure constantly monitor movement, temperature, and stress, turning the bridge into a living system rather than a static object. Driving across the Millau Viaduct is an exercise in detachment. The valley drops away. The sense of height is softened by the bridge's transparency. There is no feeling of domination, only passage. The project redefined how megastructures could coexist with sensitive landscapes. It proved that scale does not require heaviness, and that infrastructure can achieve authority through precision and restraint, rather than bulk. The Millau Viaduct is not a monument to power. It is a demonstration of discipline, where engineering serves geography and ambition is expressed through elegance. In the quiet space between sky and valley, the bridge does not announce itself. It simply endures. The Karakoram Highway is not a road in the conventional sense. It is a negotiation with geology. Stretching over 1,300 kilometers between Pakistan and China, The highway cuts through one of the most unstable mountain systems on Earth. The Karakoram Range is young, rising, and violent, where tectonic plates collide, glaciers advance and retreat, and landslides rewrite terrain without warning. Building here was never about speed, it was about survival. Construction began in the 1960 seconds and continued for nearly 2 decades. More than 20,000 workers labored at altitudes exceeding 4,700 meters, where oxygen thins and machinery loses efficiency. Hundreds died from avalanches, rock falls, and exposure. The road was carved by controlled explosions, hand tools, and sheer persistence. The highway crosses regions where mountains are still forming. Rock faces fracture constantly. Entire sections must be rebuilt after earthquakes or glacial floods. Engineers responded not with permanence, but with adaptability bridges designed for replacement, slopes reinforced with flexible barriers, and routes adjusted as the land shifts. At its highest point, near the Kunjarab Pass, the road becomes less an infrastructure and more a boundary between climates, cultures, and ecosystems. Glaciers hang above the asphalt, rivers churn thousands of meters below. There are no guardrails in many sections, only trust in the line that has been drawn. Beyond engineering, the highway is strategic. It links Central Asia, South Asia, and Western China into a single overland corridor, forming the backbone of modern trade and geopolitical movement. What once took weeks through mountain passes can now be crossed in days. Driving the Karakoram Highway does not feel like travel, it feels like exposure. This road does not dominate the mountains. It threads through them, accepting risk as a constant condition. The Karakoram Highway stands as a reminder that some megaprojects are not about conquering nature. They are about coexisting with forces that refuse to be controlled. Yaxi Expressway is not defined by distance. It is defined by elevation, exposure, and control. Cutting through the Hengduan Mountains of Sichuan, this 240-kilometer highway traverses one of China's most geologically volatile regions. Steep valleys, active fault lines, landslides, heavy snowfall, and sudden fog make the terrain hostile to continuous road infrastructure. Here, the challenge was not speed, it was stability across extremes. More than half of the expressway runs on bridges or through tunnels. Over 270 bridges and 25 tunnels lift the roadway above ravines and push it through mountains rather than around them. In many sections, the road never truly touches the land. It hovers, suspended between slopes that cannot be trusted to remain intact. Engineering decisions were driven by risk modeling rather than geometry. Three-dimensional geological mapping guided tunnel alignment to avoid fracture zones. Piers were anchored deep into bedrock to withstand seismic movement. Slopes were reinforced with flexible netting and drainage systems designed to release pressure rather than resist it. Weather is the constant adversary. The route passes through cloud belts, where visibility can collapse without warning. Sensors embedded along the expressway monitor wind, temperature, ice formation, and ground movement in real time. Traffic flow is adjusted dynamically. In extreme conditions, sections close automatically. Human judgment is no longer fast enough at this scale. Before Yaxi Expressway, the journey between Ya'an and Xichang took more than 10 hours along narrow mountain roads, prone to collapse. The expressway reduced that time by more than half, transforming regional logistics, emergency access, and economic integration in southwestern China. Driving Yaxi does not feel fast. It feels suspended. Mountains fall away beneath the roadway. Clouds slide past at eye level. The road appears and disappears into rock, mist, and steel. Yaxi Expressway belongs to the hostile terrain layer of mega projects, where infrastructure survives not by overpowering nature, but by constantly measuring, adjusting, and yielding to it. This is not a road built on land. It is a system built above uncertainty. The Falkirk wheel does not conquer space, it rearranges it. Located in central Scotland, the structure connects two canals, separated by a 35-meter height difference, a problem that once required a long series of locks. Instead of repeating the past, engineers replaced vertical struggle with rotational balance. Standing 35 meters tall and weighing around 1,200 tons, the wheel is the world's only rotating boat lift. Its design is deceptively simple. Two opposing gondolas rotate around a central axis, raising and lowering vessels through a half-turn that takes less than 5 minutes. What appears theatrical is, in fact, an application of pure physics. The system operates on hydrostatic equilibrium. Each gondola always carries the same weight, regardless of how many boats are inside. Water displacement ensures balance. Because the loads cancel each other out, the energy required to rotate the entire structure is remarkably small, roughly equivalent to boiling a few household kettles. This efficiency is intentional. The Falkirk wheel was built as the centerpiece of a larger canal restoration project, designed not to dominate the landscape, but to revive it. The structure's curved steel arms echo Celtic forms, integrating modern engineering with cultural memory rather than erasing it. Unlike megaprojects measured in kilometers or gigawatts, the wheel operates at human scale. Boats drift calmly into place. The rotation is smooth and silent. Passengers feel no acceleration, only a gentle change in perspective as water and sky exchange positions. The Falkirk wheel belongs to a rare category of megastructures where complexity is hidden behind elegance. There are no massive foundations, no brutal confrontation with terrain. The solution is intellectual rather than forceful. In an era of colossal infrastructure, the wheel delivers a different message. That progress does not always require greater power. Sometimes it requires better balance. By turning a problem of height into a question of symmetry, the Falkirk wheel proves that the most enduring megaprojects are not those that overwhelm nature, but those that quietly align with it. The Three Gorges Dam is not just a structure, it is a reprogramming of a river. Built across the Yangtze River in central China, the dam represents the largest hydroelectric project ever attempted. Rising 181 meters and stretching more than 2.3 kilometers across the valley, it converts the kinetic force of one of the world's most powerful rivers into electricity, control, and predictability. Its scale defies intuitive measurement. The reservoir extends over 600 kilometers upstream, reshaping entire landscapes and submerging cities, farmland, and archaeological sites beneath a managed waterline. More than 1 million people were relocated not as a side effect, but as a prerequisite of operation. At the core of the dam are 32 massive turbines, each capable of generating around 700 megawatts of power. Together, they form an energy engine that supplies electricity to tens of millions of homes and stabilizes national power grids. But energy is only one function. Flood control was the original justification. The Yangtze's seasonal surges had devastated downstream populations for centuries. By regulating flow, the dam transformed chaos into schedule. Shipping locks and a vertical ship lift allow cargo vessels to bypass the elevation difference, turning an unpredictable river into a navigable industrial corridor. Engineering here is not static. Thousands of sensors monitor pressure, temperature, vibration, and structural stress around the clock. The dam behaves like a living system, constantly adjusting gates and flows in response to rainfall, sediment load, and upstream conditions. Yet the cost is irreversible. Sediment accumulation alters ecosystems. Landslide risks increase along the reservoir's edge. Seismic activity, though debated, remains a persistent concern. The river continues to respond in ways that models cannot fully predict. The Three Gorges Dam belongs to the control of nature layer of mega projects, where human systems attempt not to adapt, but to command. Standing on its crest, the scale is silent. The water waits. The turbines hum unseen. This is not a victory over nature. It is a contract written at continental scale, one that must be honored, monitored, and maintained without pause. Because once a river is reprogrammed, there is no return to default. Itaipu Dam is not defined by height or spectacle. It is defined by cooperation at industrial scale. Spanning the Paraná River on the border between Brazil and Paraguay, Itaipu was conceived to solve two problems simultaneously: harness one of South America's most powerful rivers and bind two nations into a shared energy future. What emerged is one of the largest hydroelectric systems ever built. Construction began in the 1,970 seconds and required a level of organization closer to wartime logistics than civil engineering. More than 40,000 workers operated around the clock. Over 12 million cubic meters of concrete were poured, enough to build dozens of large cities. Entire sections of the river were temporarily diverted to expose bedrock for foundations. An intervention so vast it could be seen from space. The dam's installed capacity exceeds 14,000 megawatts. In peak years, Itaipu has produced more electricity than any other power plant on Earth, supplying the majority of Paraguay's power and a significant share of Brazil's. Energy flows here are not national. They are shared, synchronized, and politically intertwined. Technically, Itaipu functions as a precision machine. Turbines, spillways, and gates are monitored continuously by real-time sensor networks, tracking pressure, vibration, and temperature. Any imbalance risks cascading failure across the system. Stability is maintained not by mass alone, but by constant feedback and adjustment. Yet, Itaipu's impact extends beyond engineering. The reservoir submerged natural wonders and displaced communities, rewriting ecosystems and human geography alike. In exchange, it delivered decades of energy security and economic leverage, particularly for Paraguay, which exports surplus electricity as a national lifeline. Itaipu belongs to the shared control layer of megaprojects. It does not dominate a river for one nation. It binds two into mutual dependence. From the crest, the water appears calm. The turbines below are unseen. This dam does not announce power through force. It exercises it through coordination, a reminder that the largest systems endure not because they are strong, but because they are managed together. Delta Works is not a single structure. It is a national survival system. Built across the southwestern Netherlands, Delta Works exists because the country itself exists below sea level. After the catastrophic North Sea flood of 1953 killed more than 1,800 people, the Dutch made a decision unlike any other. They would no longer merely react to the sea. They would engineer certainty against it. The project unfolded over 4 decades, forming a vast network of dams, storm surge barriers, sluices, and reinforced dikes stretching more than 25 kilometers. Its goal was simple in concept and extreme in execution: shorten the coastline, control tidal forces, and reduce flood risk to near zero for millions of people. The engineering challenge was unprecedented. Gates weighing up to 18,000 tons had to remain open most of the year to preserve saltwater ecosystems, then close flawlessly within hours during storm surges. Hydraulic arms, real-time sensors, and predictive models constantly evaluate wind, pressure, and sea level before any movement is triggered. At the heart of Delta Works lies the Oosterschelde storm surge barrier, a structure that behaves less like a wall and more like a living machine. It does not block the sea permanently. It negotiates with it. Delta Works redefined flood defense philosophy worldwide. Instead of brute resistance, it introduced adaptive control, accepting that nature cannot be defeated, only managed intelligently. This approach has since influenced coastal protection strategies from New Orleans to Shanghai. But the system also carries weight beyond engineering. It represents a social contract, massive public investment, long-term planning, and collective trust in expertise over generations. Few nations attempt projects whose benefits will only fully reveal themselves decades later, often during disasters that never happen. From above, DeltaWorks appears calm. Water flows, ships pass, life continues. That is the point. DeltaWorks does not celebrate conquest over nature. It represents a different form of power, the power to endure, to adapt, and to live permanently on the edge of the sea, without retreating from it. The Panama Canal is not merely a passage of water, it is a reprogramming of the planet's trade routes. Cut through the narrow waist of Central America, the canal collapsed the distance between the Atlantic and Pacific Oceans. Ships that once faced an 8,000 nautical mile journey around Cape Horn were suddenly rerouted through an artificial corridor only 82 kilometers long. Global geography changed, not by nature, but by design. Completed in 1914, after decades of failed attempts, disease, and human loss, the canal demanded a new form of engineering logic. Instead of carving a sea-level trench through mountains and jungle, engineers built a system of locks and lakes, lifting ships up to Gatun Lake, then lowering them back to sea level on the opposite side. Gravity, water balance, and precision replaced brute excavation. At its peak construction phase, more than 40,000 workers operated in one of the most hostile environments on Earth. Malaria and yellow fever killed thousands before modern medical interventions finally stabilized the workforce. The canal is as much a victory of public health and logistics as it is of concrete and steel. For over a century, the Panama Canal has functioned as a global choke point. Roughly 5–6% of world maritime trade passes through it annually. Every delay, drought, or accident reverberates across supply chains, energy markets, and food prices worldwide. In the 21st century, the canal entered a new phase of vulnerability. Climate-driven droughts lowered freshwater levels, limiting ship traffic and exposing a hidden truth. Even the most powerful infrastructure depends on fragile natural systems. The 2016 expansion added larger locks, but it also increased dependence on water that cannot be easily replaced. Politically, the canal stands as a symbol of sovereignty reclaimed. Its transfer to Panama in 1999 marked the end of foreign control over one of the world's most strategic assets. From above, ships move slowly between continents. Below, valves open, gates close, and water rises on command. The Panama Canal is not a monument to speed. It is a monument to control, where timing, balance, and restraint move the world more effectively than force ever could. The Suez Canal is not an engineering shortcut. It is a pressure point of global civilization. Carved through the Egyptian desert, the canal links the Mediterranean Sea directly to the Red Sea, eliminating the need for ships to circle Africa. When it opened in 1869, It erased more than 6,000 kilometers from the Europe-Asia trade route and permanently altered the balance of global commerce. Unlike the Panama Canal, Suez operates without locks. Both seas sit at nearly the same level, allowing ships to pass through a straight, sea-level corridor, 193 kilometers long. This simplicity, however, demanded relentless excavation. Millions of cubic meters of sand were removed by hand long before modern machinery existed, at the cost of enormous human suffering. From the beginning, Suez was never just infrastructure, it was power made visible. Control of the canal meant control over imperial supply lines, oil transport, and naval movement. This reality erupted in 1956, when Egypt nationalized the canal, triggering an international crisis that revealed how deeply global systems depended on this narrow strip of water. In the modern era, Suez remains one of the world's most critical maritime arteries. Around 12–15% of global trade and nearly a third of container traffic pass through it each year. Any disruption instantly ripples through energy prices, food supply chains, and manufacturing schedules across continents. That fragility was exposed in 2021 when a single container ship ran aground, blocking the canal for 6 days. Hundreds of vessels stalled, billions of dollars in trade froze. The incident demonstrated a sobering truth. Global systems are only as resilient as their narrowest passage. Egypt's 2015 expansion created parallel channels, allowing two-way traffic and reducing congestion. Yet, even expanded, the canal cannot escape its strategic vulnerability. It remains a linear system, fast, efficient, and inherently exposed. From above, the Suez Canal appears calm and orderly. Ships glide forward in disciplined lines. But beneath that surface lies a constant tension. The Suez Canal does not dominate the world. It concentrates it, proving that in global systems, power often resides not in size, but in the ability to stop everything at once. The South-North Water Transfer Project is not a monument you can stand on. It is a re-engineering of geography itself. China's economic core lies in the north, where rivers run thin and aquifers collapse under pressure. Its water, however, flows mostly in the south. The project was conceived to correct this imbalance, not temporarily, but structurally, by redirecting water across entire river basins on a continental scale. Planned in 3 massive routes, eastern, central, and western, the system stretches more than 1,700 kilometers. It moves water from the Yangtze River Basin toward the arid north, supplying megacities such as Beijing and Tianjin, while stabilizing agriculture and industry across multiple provinces. No single dam or canal defines the project. Its power lies in networked continuity. Construction began in the early 2000s after decades of research, debate, and political commitment. The central route alone required elevating water across watersheds using gravity-fed channels calibrated with millimeter precision. Entire villages were relocated. Landscapes were redrawn. Water was treated not as a natural flow, but as a national asset under command. Technically, the system functions as a living organism. Sensors monitor flow rate, pressure, contamination, and seasonal demand in real time. Gates adjust constantly to maintain balance. A failure at one node risks downstream consequences hundreds of kilometers away. The project's benefits are undeniable. Tens of millions gained reliable access to clean water. Groundwater extraction slowed. Urban collapse was avoided. Yet the cost is equally structural. Southern ecosystems bear increased strain. Interbasin transfer introduces long-term ecological uncertainty. Once water is rerouted, reversal becomes politically and technically impossible. The South-North Water Transfer Project occupies the resource control layer of megaprojects. It does not produce energy or shorten distance. It reallocates survival. From the surface, canals appear quiet. No turbines roar, no walls dominate the skyline. But beneath that calm flows a decision of scale rarely attempted, that a nation can move rivers to preserve itself. The Mohammed bin Rashid Al Maktoum Solar Park is not built to dominate the desert. It is built to outlast it. Located on the outskirts of Dubai, this vast solar complex represents a strategic pivot by a nation long defined by oil. Instead of extracting energy from beneath the sand, the UAE chose to harvest what the desert delivers every day in excess: sunlight. Planned as the largest single-site solar park in the world, the project is designed to reach a capacity of 5,000 megawatts by the early 2030s. It combines photovoltaic panels with concentrated solar power towers, creating a hybrid system capable of generating electricity both day and night. At its center rises a solar tower over 260 meters tall, surrounded by thousands of mirrors that track the sun with algorithmic precision. The engineering challenge here is not scale alone, it is endurance. Temperatures regularly exceed 45 degrees Celsius. Sandstorms reduce visibility to near zero. Dust accumulation can cripple efficiency. To survive, the park relies on automated cleaning systems, heat-resistant materials, and AI-driven performance optimization that adjusts output minute by minute. Unlike fossil fuel infrastructure, this system has no moving supply chain. No tankers, no pipelines. Energy arrives directly from the sky, converted and stored on site. That simplicity is its strategic strength. Economically, the solar park anchors the UAE's long-term transition under Vision 2030 and beyond. Record low electricity prices achieved here redefined global solar economics, proving renewables could compete not just environmentally, but financially at industrial scale. Geopolitically, the project signals foresight. In a future where hydrocarbons lose leverage, energy leadership will belong to those who control generation, technology, storage, and grid intelligence. The solar park is not a replacement for oil wealth. It is a hedge against its decline. From above, the desert glows silver. Millions of panels reflect the sun back into the sky. This is not a spectacle of height or force. It is a statement of direction. That power, in the next era, will belong to those who learn how to extract permanence from something as fleeting as light. The Svalbard Global Seed Vault is not designed to impress. It is designed to remain. Hidden deep inside a mountain on the Norwegian island of Spitsbergen, the vault exists far from borders, conflict zones, and population centers. Its purpose is singular and absolute: to safeguard the genetic foundation of human food in case the world fails elsewhere. Opened in 2008, the vault functions as a global backup system for agriculture. Each participating nation deposits seed samples under its own ownership, sealed and untouched unless catastrophe demands retrieval. No one can access another country's collection. Control is decentralized. Survival is shared. The engineering logic is minimal by design. The vault relies on Arctic permafrost as a natural refrigeration system, maintaining temperatures well below freezing even if all power fails. Steel doors, reinforced concrete tunnels, and redundant security layers protect a storage capacity of up to 4.5 million seed varieties, enough to preserve the biodiversity of nearly every major food crop on Earth. This is not a response to a single threat. It is preparation for unknown failure: climate collapse, war, disease, system error. The vault assumes that no model is perfect, no civilization permanent, and no supply chain immune. Ironically, even the vault has faced change. As Arctic temperatures rose faster than expected, engineers reinforced drainage systems and waterproofed access tunnels, proof that even humanity's fallback plans must adapt to a shifting planet. The seed vault operates quietly. There are no daily visitors, no output metrics, no visible returns. Its value lies entirely in what it prevents: irreversible loss. Unlike energy plants or transport corridors, the vault produces nothing. It preserves potential. From the outside, it appears as a simple concrete wedge against ice and rock. Inside, it holds centuries of selective knowledge encoded in living matter. The Svalbard Global Seed Vault belongs to the existential layer of megaprojects. It is not built for growth, profit, or power. It is built for the moment when everything else fails, and humanity must begin again. From seeds, it chose not to lose. The port of Shanghai is not a harbor. It is a machine for global circulation. As the world's busiest port for more than a decade, Shanghai handles over 40 million TEUs annually, containers moving between factories, markets, and consumers across every continent. But its true breakthrough lies offshore, at Yangshan Deepwater Port, where geography was rewritten to keep global trade moving. Shanghai's natural coastline is shallow, unsuited for the largest modern container ships. Instead of accepting this limit, China built a port on a chain of offshore islands, then connected it to the mainland with the 32-kilometer Donghai Bridge. Deep water was not found. It was accessed through engineering. Yangshan operates as a fully integrated logistics system. Automated cranes load and unload ships without human drivers. Autonomous vehicles move containers across terminals in choreographed sequences. AI systems optimize berth allocation, traffic flow, and customs clearance in real time. Human intervention is minimal. Precision is constant. This level of automation is not aesthetic, it is strategic. Every hour, saved compounds across thousands of vessels and millions of shipments. The port functions 24 hours a day, largely independent of labor constraints, weather variation, or fatigue. Efficiency here is not incremental, it is systemic. Economically, the port anchors China's manufacturing dominance and its Belt and Road maritime network. More than 7% of Shanghai's GDP is tied directly to port activity. Any disruption would echo through supply chains worldwide, from electronics to energy to food. Yet the port also represents vulnerability. Concentration creates leverage, but also exposure, congestion, cyber disruption, or geopolitical tension at this node would ripple instantly across the global economy. From above, Yangshan appears orderly, rows of containers, silent machines, endless motion, no chaos, no crowds. The port of Shanghai belongs to the infrastructure of power layer. It does not conquer land or sea, it organizes flow. And in a globalized world, control over movement is control over everything that depends on it. The Riyadh Metro is not simply a transportation system, it is a re-engineering of urban behavior. Built in a city long shaped by automobiles, highways, and extreme heat, the metro represents Saudi Arabia's attempt to redesign how a modern capital moves, breathes, and grows. Spanning more than 176 kilometers across 6 fully automated lines, it is the largest driverless metro system ever constructed in a single phase. The challenge was not distance, it was environment. Riyadh's summer temperatures exceed 45 degrees Celsius. Dust storms disrupt visibility. Urban sprawl stretches relentlessly outward. To function here, the system required sealed stations, climate-controlled platforms, and rolling stock engineered to operate continuously under thermal stress. Every train runs without a driver. A centralized AI-based control center monitors thousands of cameras, sensors, and signaling nodes in real time, adjusting speed, spacing, and power use with machine precision. Human error is minimized by design. Reliability is the product. Architecturally, the metro is also symbolic. Stations were designed by global firms to act as civic anchors, places meant to reshape public space rather than merely move passengers. The system integrates buses, park-and-ride hubs, and pedestrian corridors into a unified mobility network. Economically, the Riyadh Metro addresses a hidden cost: time. Traffic congestion drained productivity, and fuel subsidies strained public budgets. By shifting millions of daily trips to electric rail, the city reduces emissions, lowers energy consumption, and delays the need for endless highway expansion. Politically, the project signals alignment with Vision 2030, less oil dependence, smarter cities, and infrastructure that supports population growth without paralysis. Mass transit becomes not just a service, but a governance tool. From above, trains glide silently beneath the desert city. No engines roar, no intersections lock. The Riyadh Metro belongs to the urban systems layer of mega-projects. It does not dominate terrain or generate power. It changes something more subtle and more difficult: how people move, how cities function, and how a society adapts when growth can no longer rely on roads alone. The Shanghai Maglev is not built for distance. It is built to demonstrate a threshold. Launched in the early 2000s, the line connects central Shanghai to Pudong International Airport over just 30 kilometers. Yet, within that short span, it achieved something no conventional railway could: sustained commercial speeds exceeding 430 kilometers per hour, making it the fastest operational passenger train in the world. The system abandons wheels entirely. Instead, electromagnetic forces lift the train several millimeters above the guideway, eliminating friction. Motion becomes a matter of controlled magnetic fields rather than mechanical contact. Acceleration is immediate. Noise fades. Vibration nearly disappears. Engineering such precision demanded absolute control. Track alignment tolerances are measured in millimeters. Power supply stability is critical. Any deviation risks destabilizing levitation itself. The result is a transport system that behaves less like rail and more like a laboratory instrument operating at city scale. Economically, the Shanghai Maglev was never intended as a mass network. Its construction cost was high. Maintenance requires specialized expertise. Instead, its value lies in signaling capability. China could absorb, adapt, and operate frontier technology at scale. The line became a proving ground. Lessons from maglev control systems, automation, and high-speed safety fed directly into China's broader rail expansion, now the largest high-speed network on Earth. What began as a showcase evolved into an accelerator of institutional knowledge. Yet limitations remain. Noise at top speed, energy demand, and integration challenges have kept maglev expansion cautious. Even China ultimately favored steel-wheel high-speed rail for national deployment. From inside the cabin, the speed display climbs past 400. The city blurs. The sensation shifts. The Shanghai Maglev belongs to the experimental frontier layer of mega-projects. It does not optimize efficiency or capacity. It asks a different question. How fast can precision be scaled before complexity outweighs advantage? In that sense, the train is less a solution than a controlled test, one that proved speed itself is not the final goal of infrastructure, but a tool whose value depends on what systems can sustain it. Hudson Yards is not a neighborhood that grew organically. It is a city assembled above reality. Rising on Manhattan's west side, Hudson Yards is the largest private real estate development in U.S. history, built not on open land, but over an active rail yard that could not stop operating for a single day. Before any tower could rise, engineers had to solve a paradox: how to build a city without touching the ground beneath it. The solution was structural choreography. Massive steel platforms were installed above the tracks, supported by columns drilled deep between live rail lines. Construction proceeded in narrow windows between train schedules. Every mistake risked paralyzing one of the busiest transit corridors in North America. The final result is a vertically integrated urban system. Office towers, luxury residences, retail space, cultural venues, and public plazas layered into a single engineered environment. Energy systems, ventilation, water reuse, and digital monitoring are centralized and optimized at district scale, not building by building. At its core, Hudson Yards functions like infrastructure disguised as architecture. Data flows manage lighting, climate, and crowd movement. Elevators behave like transit nodes. The development does not merely house people, it coordinates them. Economically, the project represents a new model of urban power, privately financed, privately governed, yet operating at city scale. With investments exceeding $25 billion, Hudson Yards reflects how capital can now design urban futures faster than public planning alone. But the project also exposes fault lines. Critics point to exclusivity, rising inequality, and a public realm shaped by private priorities. Hudson Yards is efficient, but not neutral. From above, glass towers reflect the Hudson River and the sky. Below, trains continue to move unseen. Hudson Yards belongs to the vertical city layer of mega projects. It does not conquer nature or redirect rivers. It builds on top of complexity, showing that in the modern age, the most ambitious structures are not those that expand outward, but those that stack systems, capital, and control into a single engineered skyline. Forest City is not a failure of engineering, it is a failure of assumption. Built on 4 artificial islands off the southern coast of Malaysia, near the Singapore border, Forest City was conceived as a futuristic smart, metropolis green, car-free, technologically advanced, and designed to house more than 700,000 residents. At an estimated cost exceeding $100 billion, it was one of the most ambitious real estate visions of the 21st century. From a technical standpoint, the project was formidable. Massive land reclamation reshaped tropical seabeds into buildable platforms. Soil stabilization systems fought erosion and saltwater intrusion. High-rise towers were designed to integrate greenery into every level, with vertical gardens, smart energy systems, and pedestrian-first layouts. On paper, Forest City represented the next evolution of urban living. But cities are not built by concrete alone. The project's core assumption was demand, specifically sustained international demand, driven by foreign buyers, particularly from China. When regulatory changes, geopolitical shifts, and capital controls tightened, that demand evaporated. What remained was infrastructure without population, scale without life. Today, only a fraction of the planned residents live there. Streets remain quiet. Towers stand partially occupied. retail spaces wait without customers. Forest City did not collapse structurally, it stalled socially and economically. The lesson is systemic. Unlike transport corridors or energy systems, cities require continuous human circulation to function. Utilities, maintenance, and governance depend on density. Without it, even the most advanced smart systems become liabilities rather than assets. Forest City also exposes the limits of top-down urban design. A city optimized for investment metrics does not automatically become a place people choose to live. Livability cannot be pre-engineered in isolation from culture, policy, and economic reality. From the air, Forest City looks pristine green towers rising from blue water. At ground level, silence dominates. Forest City belongs to the overextension layer of mega-projects. It proves that ambition, when detached from demand, creates monuments not to the future, but to miscalculation. In the age of megastructures, the hardest thing to build is not scale. It is sustained human presence. The International Space Station is not a monument to height or mass. It is a monument to coordination. Orbiting Earth at roughly 400 kilometers above the surface, the ISS is the largest structure ever assembled in space. Construction began in 1998 and continued for more than a decade, involving 5 space agencies: NASA, Roscosmos, ESA, JAXA, and CSA, and dozens of launch missions. No single nation could have built it alone. From an engineering perspective, the ISS defies conventional construction logic. Every module was launched separately, then assembled in microgravity, where tools behave differently, materials expand unpredictably, and mistakes cannot be corrected easily. Astronauts performed hundreds of spacewalks, connecting power, life support, data, and thermal systems piece by piece, often improvising solutions in orbit. The station spans over 100 meters, weighs more than 420 metric tons, and travels at 28,000 kilometers per hour, circling Earth every 90 minutes. Its solar arrays generate about 90 kilowatts of power, sustaining laboratories, habitats, and life support systems for crews rotating every 6 months. But the ISS is not defined by scale alone. It functions as a permanent human presence beyond Earth, testing how the body, mind, and technology behave away from gravity. Thousands of experiments have reshaped medicine, materials science, fluid dynamics, and climate observation. Many systems used today, water recycling, closed-loop air control, autonomous monitoring, were refined aboard the station. Yet, the ISS also represents a transitional era. It is expensive to maintain. Aging modules require constant repair to political cooperation. That once sustained it has grown fragile. Plans now point toward retirement in the 2030s, with controlled deorbiting into the Pacific. The ISS occupies a unique layer of megaproject history. Not profit-driven, not territorial, not permanent. It proved that humanity can build and live beyond Earth, but only through shared trust, long-term vision, and relentless precision. Above the planet, the ISS reminds us the greatest structure humans ever built. was not owned by anyone and could not exist without everyone. The James Webb Space Telescope is not built to observe space as it is. It is built to observe time. Positioned nearly 1.5 million kilometers from Earth at the second Lagrange point L2, JWST operates where gravitational forces balance and thermal conditions remain stable. From this distant, silent orbit, it looks backward, detecting light that has traveled over 13 billion years, revealing the universe as it existed shortly after the Big Bang. Engineering the telescope required abandoning nearly every rule of traditional spacecraft design. JWST could not fit inside any existing rocket fully assembled. Instead, it was launched in 2,021 inches, a tightly folded configuration, then unfolded itself through over 300 single-point deployment steps, each one irreversible. A single failure would have ended the mission. At its core is a 6.5-meter primary mirror, composed of 18 hexagonal segments coated in gold to maximize infrared reflectivity. Together, they collect more than 7 times the light of the Hubble Space Telescope. But light alone is not enough. To detect faint infrared signals, Webb must remain extraordinarily cold. Its 5-layer sun shield, the size of a tennis court, blocks heat from the sun, Earth, and Moon, keeping instruments below 233 degrees Celsius. On the warm side, temperatures exceed plus 100 degrees Celsius. Between them, precision materials and tension control maintain a thermal boundary thinner than paper. JWST is not serviced. It was designed to work perfectly the first time. Its scientific purpose spans multiple frontiers, probing the atmospheres of exoplanets, mapping star formation inside dust clouds, and identifying the chemical signatures of early galaxies. For the first time, scientists can analyze water vapor, carbon dioxide, and organic molecules on worlds beyond the solar system. But JWST also marks a shift in human ambition. At a cost of nearly $10 billion, built through collaboration between NASA, ESA, and CSA, it represents a collective decision to prioritize knowledge over proximity and patience over speed. The James Webb Space Telescope does not orbit Earth. It orbits possibility, quietly extending the boundary of what humanity can see and how far back we are willing to look to understand ourselves. The vehicle assembly building is not a factory. It is a volume of space engineered for ambition. Rising 160 meters above the Florida coast at NASA's Kennedy Space Center, the VAB was built in the 1,960 seconds to assemble rockets larger than anything humanity had ever attempted. Its purpose was singular: to prepare machines powerful enough to escape Earth. Measured by volume, it remains one of the largest buildings ever constructed. Inside, its interior space exceeds 3.6 million cubic meters, so vast that clouds can form near the ceiling on humid days, and rain has been recorded inside the structure itself. The doors alone are monumental, 139 meters tall, opening vertically in sections, each movement slow and deliberate, like the unveiling of a cathedral. The building was designed around precision under extreme scale. Saturn V rockets 110 meters tall were stacked vertically inside using overhead cranes, capable of lifting 325 tons with millimeter accuracy. Later, the space shuttle was integrated here, its external tank and solid rocket boosters aligned under strict structural tolerances that allowed no deviation. Nothing inside the VAB moves quickly. Mass dictates rhythm. The floor houses 4 high bays, each reinforced to support the weight and vibration of fully assembled launch vehicles. Embedded rails connect directly to the launch pads via crawler transporters machines, so heavy they compress the ground beneath them as they move at walking speed. Unlike many megastructures, the VAB is not static history. It continues to evolve. Today, it supports NASA's Space Launch System, SLS, and future deep space missions, adapting its internal platforms for rockets designed to travel beyond low Earth orbit. Every modification respects a core constraint. The building must accommodate vehicles not yet fully imagined. The vehicle assembly building embodies a specific moment in human thinking when scale was no longer a byproduct of ambition, but a prerequisite. It stands as proof that before humanity could leave Earth, it first had to build a space big enough to assemble the idea. Starship is not designed to reach space. It is designed to stay there and then go farther. Standing over 120 meters tall, when fully stacked with its super heavy booster, Starship is the most powerful launch system ever built. At liftoff, it generates more thrust than the Saturn V and Space Shuttle combined, redefining the physical limits of rocketry. But power is only the surface. What makes Starship radical is not its size, it is its philosophy. Unlike every major rocket before it, Starship is engineered to be fully reusable both stages. The Super Heavy booster returns to the launch site minutes after liftoff, while the upper stage Starship is designed to re-enter Earth's atmosphere, survive extreme heating, and land vertically. In theory, the same vehicle can fly again within hours. This changes the economics of space. Constructed primarily from stainless steel, Starship rejects lightweight aerospace tradition in favor of durability, heat tolerance, and rapid manufacturing. Steel allows the vehicle to withstand temperatures exceeding 1,400 degrees Celsius, simplifying heat shield design and reducing cost. Entire prototypes are built, tested, destroyed, and rebuilt in months, sometimes weeks, at SpaceX's Starbase facility in Texas. Starship is intended to carry over 100 tons of payload, or up to 100 people at a time. Its mission profile extends far beyond Earth orbit. Satellite megaconstellations, lunar cargo under NASA's Artemis program, and eventually human settlement on Mars. No previous spacecraft has been designed with permanent off-world habitation as a primary objective, but the system remains experimental. Test flights have ended in controlled splashdowns, hard landings, and high-altitude explosions, each treated not as failure, but as data. Starship follows an iterative model, more common in software than aerospace. Launch early, break things, improve fast. Starship represents a shift in human engineering culture, from scarcity to repetition, from caution to iteration, from reaching space as an event to treating it as infrastructure. If it succeeds, Starship will not be remembered as a rocket, it will be remembered as the moment space stopped being distant and became operational. Across continents, oceans, deserts, and even beyond Earth itself, these megastructures reveal a single pattern. Humanity no longer builds only to survive. It builds to extend control over scale, distance, and time. Bridges no longer simply connect shores. They compress economies. Dams no longer just stop water. They regulate nations. Skyscrapers no longer house people. They project intent. And machines like Starship or the James Webb Telescope are not destinations. They are statements of trajectory. Yet every project carries tension beneath its precision. Maintenance battles erosion. Energy systems depend on fragile balance. Cities built faster than demand can hollow out. Even the most advanced technology remains exposed to climate, politics, and human decision-making. What defines these megaprojects is not perfection, but commitment. Decades of planning, millions of components, billions of dollars, and a willingness to accept risk at civilizational scale. This is not the age of isolated monuments. It is the age of systems interlinked, automated, optimized, and vulnerable. The future will not be shaped by a single tower, dam, or spacecraft. It will be shaped by how these structures interact with the planet and with each other. Megaprojects do not ask whether humans can build bigger. They quietly ask something more difficult. Can intelligence scale faster than ambition? The answer will define not how high we build, but how long what we build continues to stand.